Hi everyone, thanks for joining us on the fifth episode of the PowerHour series, presented by Scanware. We've been covering this for one a month now, covering electrical asset management. So those that don't know me, I'm Daniel Henderson. I'm a chartered electrical engineer based in the UK, with I suppose, quite a wide background. Hopefully you know me by now. And today we're going to be looking at electrical incident investigation and root cause analysis, particularly on a real example, which is a high voltage transformer failure. And I'm joined today by two industry professionals. So I've got Cody Fleming and Johnny Giff. I'll now pass you over to them to get some introductions done. There you go.
All right. Good morning, everybody. My name is Cody Fleming. I work currently as an operations electrical subject matter expert for Align Data Centers, hyperscaler provider for different vendors, different customers. In the past, I was a Navy nuke electrician, did that for 10 years, and I went into the civilian side of nuclear power. And then from there, I spent time at Amazon as a technician and then a chief engineer and made my way here into Align Data Center. So sum total about 16 years of various operational fields. Yeah, Navy nukes, that's right. Nuke power.
Well, good morning, everyone, or good afternoon, depending where you're joining us from. I'm Johnny Giff, also a chartered electrical engineer. I'm based in Scotland, as I'm sure most of you could tell by the accent. I set up my consultancy business, split up the Spindrift 18 months ago now, focused on electrical safety after 20 years in the corporate world. My background was originally as an operational engineer, working on the distribution and transmission networks here in Scotland. I then moved through the ranks in various guises and roles in that world before finishing up in the renewables industry, looking after the electrical networks for a large portfolio of wind assets, which moved on to battery and solar just before I left. But as I say, for 18 months now, I've been working as an independent contractor, supporting many industries with their safe systems of work, one of which is Scanware, hence why I'm here today. So hopefully you all enjoy the webinar and hopefully get something from it. So thank you for joining. I'll pass back to Dan.
Perfect. So the only civilian on the panel today, Johnny, both Cody and I ex-Navy. We did have a third guy who was ex-Navy as well, but he couldn't make it, unfortunately, which is probably good for the numbers, even that up as well. Or military to civilian ratio. There's probably a joke tucked in there somewhere as well, you know, an
Something.
American
Yeah, there's got to be something in
Englishman and a
there.
Scotsman. There's got to be. But yeah, we'll avoid that HR nightmare. So just some house rules again that we normally go through. So after the webinar, if you've registered, you will receive the slides via email. You'll also get a recording sent as well after the webinar. And there will be a post-webinar survey. Tell us how we did. Again, we've covered the topics that we think are pertinent. If there's anything that you want to look at differently, again, let us know. Use the Q&A. So there won't be polls as such today, but there will be we will be wanting your opinions put across as well. So yeah, they're the gist of the ones that we've covered typically. So just to recap on the series overview that we've covered so far, it's quite a wide topic, electrical safety, and the way we've tried to focus this on is if you're going into the role or if you're involved in management of electrical networks. So whether you're a qualified electrical worker, an energy marshal, a duty holder, or electrical responsible person, there'll be someone that's responsible for electrical networks, and sometimes it can be quite daunting, especially in the wide industries that we cover, in FM and heavy industry and renewables. Often you might not have all of the required knowledge and experience to go with that. So we've tried to look at it with that approach of a step-by-step, bite-sized pieces of things to do to best manage your electrical network and make sure it's safe to control, operate, and maintain for you and your people and your business. So just to recap, we looked at starting off when you've just gone into a business doing this and building your asset lists, using that data to build out your maintenance plans and business impact assessments based on any operational restrictions and what they were, and obviously any obsolescence, and then trying to prioritize your maintenance. We then took that to the next step on the next one, looking at typical electrical maintenance in line with sort of NFPA 70B, and then cross-referencing that against manufacturers' O&M manuals to see where those grey areas exist between NFPA 70B as a typical standard on a risk-based approach and between the manuals. We then went a bit deeper, looking at understanding the results from transformer oil samples, which to me is a riveting topic, but might not be for everybody. But that was a good understanding of interpreting the data, how the results come about and what can impact those, and then how that impacts your electrical safety and reliability of your network. And then the last session that we did was looking at protection studies, looking at that, the coordination, fault levels, and then instant energy analysis for arc flash, and how they kind of all interact, changes that you can make, mitigation, and then how the outputs of those impact the electrical safety of people on your network. So now we're here finishing off the year with looking through what happens when things do go wrong, and the approach to take when you're going through that investigation process. Again, it will vary and it might be different by company basis. You might have your own standards, but this is a typical approach. I've got a series for 2026. It's just been finalized. So we'll announce that on our social media in January, just with what's coming up in the series. But again, that's not 100% set in stone. So in the Q&A, or in the chat, sorry, or in the poll at the end, if there's specific topics that are pertinent to people that they want to know about, or they want us to get industry professionals in to discuss, let us know, then we could potentially tailor that to suit as well. So learn objectives of today, again, it's going to be looser than normal, with it being a bit more of a discussion. We're going to look to understand potential causes of HV transformer failure, the mitigation applied to reduce or prevent these asset failures, and then understand the process applied to determine the cause of failure. So the way this is going to work is this is based on a real world example when I was an electrical responsible person for an electrical network in heavy industry in a production facility. So this is based on a real example. We'll try to link, some of it so it can't be taken back to the business, but essentially it's probably relatable for most people. So in this, I'm still going to be being the duty holder in this session, and there will be an issue that occurs on my network where I need help from others to try and work through what that root cause is. So it's, as I mentioned, it's a heavy industry production facility. There are 500 plus employees on my site working 24-hour operation over a 5-shift pattern. The infrastructure varies in age. So from 1970s, the original build, and it's been expanded, enhanced, upgraded over time. So you've got things that are brand new, and you've got other areas that are, and that ranges across infrastructure to the production equipment. From my personal responsibilities from an electrical perspective, I've got a 66 kV electrical network, and then distributed at 11 kV, some 6.6 kV and some 3.3 for some of the heavy process equipment, made up of 45 high voltage transformers ranging from 500 kVA to 12 MVA. So there's a range of sizes in there. Just a bit of an overview of the area in question where we're going to be looking. I know this is an aerial view and it's probably not ideal, but this building is the edge of the factory. This is the next edge of the factory. This here is the powerhouse, or the boiler house. I've got a 11 kV substation in this area under the roof. We've got outdoor high voltage transformer compounds, so transformers here, adjacent to the powerhouse, where we've got a couple of steam boilers. This framework here has got some high pressure steam, high pressure condensate, high pressure air. And this area here is a main walkway for people walking into the factory and into the powerhouse, and also a forklift truck route as well, taking product from one end to another. So it's quite heavily used walking past these transformer bays. Just to give a bit more context, this is a street view looking up that roadway into the factory. These are the transformers that we're going to be talking about right next to the high pressure steam line. And you can just see there that it's quite accessible for people to walk past. And this is a image of one of the transformers. So just to give some context on the network, I've got 2 grid connections at 66 kV. These are my assets under my control. these are 66 kV. They are 12 to 24 MVA, and they're capable of managing the whole site load on one of those. So the site's been constructed with N+1 from a reliability perspective. So in the event of a fault or maintenance, I can put all the load onto one transformer and take the other transformer offline to do maintenance or conduct a repair. I've got the original switchboard is this one, which is 11 kV. You'll see the setup where you've got an incomer, and then it's in two sections via a buzz tie. And you'll see, if you just kind of have a quick look, most switchboards which are critical, like this one here, you've got a supply from each side of that board, giving you that N+1 capability, everything sized so that you can buzz couple in the event of maintenance or a failure, from anything from a full side of a board just to an individual circuit breaker. And that's the same on this side. I've got another 11 kV switchboard and all the downstream distribution from there. What I will add to this is that we do have an interconnecting ring going from this 11 kV switchboard across the another 11 kV switchboard. So the original design would have been having that as an only open point, but there had been some recent power quality issues off-site. Up network, there were some overhead lines where they were getting some debris impacting on the overhead lines, which was then causing power dips on the site. So this was closed, and it had been for a number of months, to allow that to reduce the impact on the network. So when you did have a dip upstream, you didn't have any impact downstream. It didn't that the voltage ride through was suitable and sufficient then to not impact our network. So the incident itself that we're going to talk through, at around 8 p.m. mid-June, the full site loses power, so everything goes off. There's 60 plus employees and contractors on site at that time, and the emergency response plan gets initiated.
Shut it down now.
Emergency lighting activated.
That's how I imagine it happened. Nakatomi Plaza there losing power from the obvious Christmas film Die Hard. I'll not put that in the poll because we'll never get through the day. We'll be discussing that all day. It's definitely a Christmas film though. The emergency duty manager was called to inform them that the power had gone out, and then as the electrical network responsible person, I was called. Essentially, I was the electrical John McClane in this example. So I was then, before I go to site, I was trying to gather as much data as I could. So I was speaking to the site shift electrician to find out what they knew, trying to understand if anything had been seen in any of the areas, speaking to the area team leaders before I even got to site, so I could try and identify if there was any issues that could identify risks to me when I get there, but also risks to people that were still on the site. The considerations that were there for the duty manager was obviously the welfare of persons. It's dark. There's 60 plus people on site. You've lost all power apart from some emergency lighting. And then there are some health and safety implications and environmental implications on this particular site, where if you don't get power back in a certain amount of time, there can be an impact there. And then finally, the customer impact. Doesn't matter what field you're in, whether it's heavy industry, production, generation, there's always going to be an impact to somebody on the end of what you're doing. So you might have a finite time of stock product, or you might have a certain amount of generation that you can't get to somebody that you've dedicated generation to. So you've got to take into consideration that customer impact, which is where myself and the duty manager are working alongside. So I've already spoke to some people to try and understand if anything had been seen, and I've got nothing back. So nobody's seen anything. So I've arrived at the security to see if CCTV had any information, or if they've seen anything on the CCTV system, which they didn't. CCTV cut off, and it was clear that there was no UPS providing that. So what I've done is, there's no indication of anything that could be a risk to me. Nobody's seen anything that could have potentially caused the fault. So I've gone to this nearest substation, which is a 66 kV to 11 kV substation, and I've identified that this circuit breaker is tripped. However, everything else in that substation, there's no signs of a breach of integrity. There's no leaks. There's no signs of overheating or damage that I can visually see. So that's tripped on overcurrent on that electromechanical relay. I've then gone to this substation over here, which is the nearest one. So I've just gone from a logistical perspective as quick as my legs can go. In this location where I've got an 11 kV switchboard, and this circuit breaker here is tripped again on overcurrent, but there's no sign of any damage. The integrity, everything looks intact. There's no signs of overheating or burning or smells. There's no indication of anything going wrong in that area. And then I've walked the whole network. So this is cables, transformers, LV circuit breakers, the downstream 6.6 and 3.3 kV switch gear and transformers, and there's no signs of any damage. So I'm fairly confident that that's all okay. I then walked to the other side of the site. It's quite a large site. It's a couple of kilometers long. And then all these transformers and LV switchboard, there's no damage, there's no signs of any flags on the relays or anything like that. I've now gone to this 11 kV switch room, and I've identified that there's this OCB here has tripped, and there's a heavy amount of carbon contamination behind and at the side of that switchboard. I've then walked further down to that compound that I showed you on the overhead view, where these transformers reside. And these transformers circle green are all fine. I've followed the cables, I've checked the LV boards, and there's no indication there. I've then got to this transformer here, which is the boil house or powerhouse transformer. And again, there's very signs of heavy carbon content on there. So I suppose as part of a process then from where I've gone from this point is, again, I've got additional support in place at this point, and I've worked through the network, testing through various of switching, safe systems of work processes, issue of safety documents, testing, visual inspections, and then I've started restoring. So I've restored this side of site first to get supplies back and get the light and small power on from a welfare perspective. And then on this side, because I know this is the area of the fault, I've taken a bit more of a measured approach. Again, a circuit at a time, testing, inspecting, and then restoring one at a time, leaving this circuit here isolated. And I've got everything on in around 6 hours. So we've got power back to site, and now we're into the stage where we need to start understanding what's gone wrong. So just for some context, this is what was found. So this is the transformer itself. This is the HV junction box. So this is 11 kV. You'll see that all of the studs on the junction box have completely torn away. On top, you'll see between two phases, you've got a hole about 2.5 inch diameter between the two phases. That's about 5 mil mild steel, that junction box. So quite a lot of heat to actually burn that through. And then this is what's left of the junction box. Again, for those that aren't familiar, this is a compound filled junction box. So the age of this transformer, it was common practice that they would make the connections and the terminations, and then they would, through this filling cap here, fill the junction box up with a bitumen-based compound, just to make it, I suppose, maintenance free. You're not going to go back in there. The connections are done, and you're not going to take them back off. At the switch gear, this is a front view with the circuit breaker removed. So you've got carbon build up inside, mainly from the circuit shutter side of that. At the rear of the board, you've got quite a lot of contamination built up. So you can see the nice red bricks how it should be. This is all damage and debris from that expanding copper, that molten metal that's been thrown around in there. And this is the rear of the junction box. Again, compound filled. You wouldn't want to be in that location if it failed. The cable, so the cable from that junction box on the switchgear to the transformer was around 100 meters, roughly, and it was like this all the way down. So that's an immense amount of heat that's gone through that to actually split the cable all the way down. That was the full length, full 100 meters. So quite a lot of damage. And then we've now got power back. So luckily, it's not the best footage, so apologies. But this is some footage from the CCTV. So in this example, this is that pipe bridge on the outside of the powerhouse that takes those steam and condensate and air lines. These are the two compounds. So this one here is the one in question, the one at the front, and this is the adjacent one for that N+1 supply. So this one's a slowed down version of the same video. Again, it's not the best, but you'll see an orange flash, lots of molten metal. Another second will pass by. Probably a bit too slow. You get the gist though. And then there's that white flash. That's your second arc there. In real time, much quicker.
You see that it happened in about 2 seconds, give or
Yeah.
take.
Yeah, so yeah, about 2 seconds, 3 seconds. And the timing on the circuit breaker that tripped, I think it ended up, was somewhere around 3 to 4 seconds. So what should have happened in that eventuality on this transformer, when that transformer did fail, your protection's going to be expected to go on this circuit breaker here. So I'd have expected this to trip. If that didn't trip from a coordination perspective, I would expect this circuit breaker to trip. If that didn't trip for whatever reason, I'd then expect this one to trip, and this one did. So it was sat at around, 3 seconds, 4 seconds, just where that trip, which is much too long for what you'd expect your coordination to do. So from my side, I've had an issue. So why did that transformer fail, and why did protection not work as expected? So it'd be good if we could. I'm going to ask for some help now from Cody and Johnny. We'll go through one section at a time. So maybe do like method first. But if anyone's got any inputs again that you think they might be, we'll talk through them and then try and rationalize what we think or what did or what didn't impact the fault. Yeah, Cody, Johnny.
Yeah. Yeah, perfect. All right, so we'll start off with method. I'm going to let Jonathan kind of go into the protection studies. He knows a good deal more about that. But on the operations side, the first thing that you do in across any industry is escalate. So they did that. They initiated your emergency plan. They contacted you. They contacted the director. Got everything going in the right direction to start restorations. So then, you can start asking the questions. Okay, when we're restored, power's restored, we're good. We have these two problems that you stated: the transformer failure and the seeming lack of coordination across your switch gears. So what do the inspections look like? Are there rounds? Did anything get missed? Or how often are they inspecting these transformers? And I've seen a couple different transformer configurations, obviously. I've seen ones oil filled with external fans. I've seen the ones that you have here, which are radiator style with natural circulation. So are they cleaning them? Are they inspecting the cabinets and whatnot? So those are the kinds of things that I'm going to start thinking about and start asking questions about for method. And I'll turn it over to Jonathan for protection.
Yeah, thanks, Cody. So yeah, given that the fault didn't clear where we expected it to clear on the circuit breaker protecting the transformer, and given the duration the fault was on the system for, I think Dan had said it was circa 3 seconds. The protection studies is obviously a good starting point. Building on what Cody said as well, when you're looking at your maintenance plans, does protection fall part of that? Dan had mentioned that these are old electromechanical relays, so you would ensure that these form part of your preventative maintenance plans, that the mechanical disc is being proven as part of your maintenance, because these can seize, as any mechanical device can do. But yeah, protection studies is a good starting point. Given the age of the site as well, it's been there for over 50 years. Every time your electrical network is either added to as the plant extends, or plant equipment is decommissioned or commissioned, there should always be a revised protection study to ensure that any changes are catered for. So yeah, I guess we'll pass to Dan based on what Cody and I said around protection studies and the preventive maintenance as a starting point for the investigation.
Yeah, so the emergency plan was enacted. I think you mentioned there was again, I think you mentioned about process and that, whether it was manual or automated. some sites will have
Yes.
triggers. Will have triggers as part of that, maybe, but not in this example. So I think again, it depends on your how advanced your technology is. So if you've got quite an advanced network where you've got some condition-based monitoring equipment and things like that in there, you might have triggers like warnings for certain things that then kick in your emergency plan, which was a good point to bring up. But for this example, I mean, there was on this site, but it was purely for production. So if you had production issues, it would flag up and then start an initiation of an emergency response. But from an infrastructure perspective, we didn't have that. So it was a case of action. Then the emergency response plan was enacted. So it was a manual process. But it was in place, I guess. The inspection side, so there were inspections. We'll probably cover that a bit more in depth, but as a matter of, I suppose, just as reference. So the process on this site was every 3 months, a inspection was done on the substations and the compounds, done by a technician, following a check sheet, looking for things like debris and housekeeping, and so it was all visual. Every 12 months, there was a partial discharge survey and a thermal survey done by a third-party contractor. And then every 4 to 5 years, there was intrusive maintenance done on the assets themselves. Protection studies, there was one done, Johnny. There was one in place. It had been done about maybe 18 months prior, but there had been some changes on the network in another area, so it wasn't fully up to date, but it was, it would have been updated once that project was finished. But yeah, you're right and totally right in what you're saying. That's why we repeat them, because if there's changes on the network, we need to know that can impact the fault levels, and at the same time, we need to verify the utility supply, so the DNO, that if they've made any changes that might impact the downstream network, we need to make sure we take them into account. Was there anything in the chat on method?
There's just one note here. So also worth checking that the protection settings at the relay match the settings in the protection study or master schedule. This issue was mentioned in the last webinar around validity of arc flash calculations.
100%, yeah, that definitely. Yeah, definitely. So on this one, I mean, we'll cover it when we go a bit deeper, but yeah, essentially, they were matched because it was done after the design was done. So it had been around a long time, so we probably had multiple studies by the time. But the settings definitely something to look at as part of this. So if we look at materials next, so these were some of the things that I was thinking that might have been an issue in there. I'll pass it back over to you guys, and on the chat, if you've got anything that you want to add in for materials, let us know.
Yeah, of course. So, as you stated, this is an old site, 50 years, 1970s equipment and so on. And so you have to consider the life of the equipment. Like it may be well inspected, maybe that you've done all the preventative maintenance, but stuff gets old. There are issues that you find, especially in this instance where you have that sealed compartment for your high voltage cables. That's not something you are going to ever open up again. It's not meant to. It's meant to be maintenance free. So that's a consideration. Power quality, what does loading look like on the transformer? Is it good quality? Like, is it imbalanced kVAR versus kVA? What kind of things are you looking at there? That kind of sums up the materials from an operations standpoint.
Yeah, definitely.
Yeah, and again, just to add on what Cody said, with most facilities, they start off of a certain size. And as production increases, as the company becomes larger, you often find that load is added to the network, and it's not always accounted for with regards to the rating of the equipment supplying the manufacturing process. So yeah, I would absolutely look at what the loading was for that transformer. Was it within its capability, or was it overworked? And if it was overworked, do we know how long it had been overworked for? Transformers do have a cyclic rating, but if that is exceeded with extensive additional load, then that will degrade the transformer over time. Yeah.
Yeah, digressing slightly, but that's an issue everywhere. The classic, loading of the assets, people adding a bit here, a bit there, and then whoever's ultimately in charge of the network or responsible for it's never informed until eventually you get to the overload point. But yeah, definitely some good considerations. We've got someone that in there, load subtraction should be also taken into account. Yeah, again, something to take into consideration as part of this, the loading element and the especially power quality as well, because obviously a lot of the networks, especially back then, were designed for direct online, so very linear loading. Whereas since then we've now been going to a lot of non-linear applications, which is a totally different type of load for the design of the network. So we look at machines next. Pass it back to you guys.
Yeah, absolutely. So, and this is where we kind of dive a little bit deeper into the transformer itself and the protection studies that Nick brought up. So, oil samples, how deep are those oil samples going? Are you doing just fluid analysis, or Daniel, do they do DGA on these as well? Are they looking for acetylene, propane, anything like that?
Good point. Yeah. So
Touched on the transformer, Nick. Go ahead, please.
yeah. So again, that is so common. So yeah, so like you say, fluid. If you're just getting fluid analysis done, you probably wouldn't have DGA, which would probably give you an indication of something not being right inside. So yeah, just we'll cover it. But for the other samples, it was a full suite. So it was your standard fluid analysis and DGA as well.
And then, we touched on the transformer maintenance. You mentioned that that had been done relatively recently. You did the partial discharge testing, and can't remember all the other tests that you mentioned, but you said it was maintained and by a third-party vendor, and you signed off on it. And then the switchgear maintenance, that's absolutely where we kind of go back into the validation of your arc flash study, or short circuit coordination study. Do the settings match? This is where we can kind of start diving into the why of how did that fault get so far up into the system. And then, your battery tripping units, how did you have control power, or were your battery tripping units, and was the breaker able to trip? Did it have the power it needed to do its job?
Yeah, really good point. So yeah, we'll cover it, but the transformer was maintained, I think like the year before. Same with the switchgear maintenance. It was kind of done, around the same time to take off that circuit, and then so done the circuit breaker first. As part of that, the switchgear, did do the electromechanical relay, making sure that it was trip time tested to the setting. The Yeah, like I said, we covered the oil samples, the transformer maintenance. You'd done what you could. Everything was, seemed to be fine. The battery tripping unit was done around the similar time, not in that same period, but it was done at a similar time. Was a older type unit, but still fairly reliable. Anything from you, Johnny?
I think we covered most there, but I think really just for our audience, an important part with maintenance, especially being a duty holder, is that when you do receive maintenance check sheets from the technicians, from the electrical fitters who was carrying out the work, is that you have some process to collect that data, analyze that data, and look for trends. So just wondering if looking at historic oil samples or maintenance records, was there anything in there that flagged up that the transformer was starting to degrade, or that the switchgear, sorry, may not operate? So was there anything in the historical data that would suggest?
Not from oil samples. So the oil samples were trended. So I used the same company, so that you kept that data going year on year. So there was no trends in oil samples, which we're gonna have a look at the latest one as we go. But yeah, there was no trends in that. Nothing on this circuit, particularly from a switchgear maintenance perspective. However, it is heavy industry, and this was I suppose you did have quite a lot of dust from this process. So not on this particular circuit, but in other substations, there were elements where you did have kind of some dust ingress, because the ingress protection rating of some of these all the electromechanical relays probably isn't as tight as some of the newer relays. So on some of them, you did have some dust ingress, which maybe impacted mechanically the operating mechanism, but the maintenance had been done the year before on this one, and there was no issues on there.
Can we quick
Joe?
segue down? There's just a quick one in the chat, if that's all right.
Mm-hmm.
It's relating to the previous one, I believe, but good to see that the thermographic and PD surveys were conducted. As an insurance risk engineer, my question will be, were the contractor's competency assessed? Was the correct procedure followed? Were the results clear to the operator? And were plans made for any findings made?
Yeah, so from the third-party contractor perspective, as part of the onboarding process, there was the verification of their competency assessments, their framework that they apply. Yeah, and on the report, it's things like, were they trained to do partial discharge? Testing, so they had their certificate of competency for that. Likewise for thermography, and you also got the calibration date and number for the actual test equipment that they were using. So not on this particular circuit, but where they have identified some slight levels of PD. So not on this circuit, but on one in the past where it had been highlighted, there had been a clear escalation plan where it was identified, documented in based on the risk, a remedial plan put in place where we isolated, interrogated, and then identified, a loose connection or slightly loose connection, which was rectified. So I wouldn't say definitely a set in stone plan, but a process that had been put in place as part of our due diligence and in line with our loss prevention and risk management processes. Yeah, so if we look at people, come up with some points there. Again, we could probably talk all day on some of these, but what do you guys?
But Jonathan, he made some good points in our discussion, so I'd like him to. Wouldn't mind taking this one, John?
Yeah, I'll kick off on this one. And I guess some of these points builds on what Richard had mentioned in the chat. You would want to look at the competency of the people carrying out the task, not just from a technical perspective, but are they familiar with the gear and the site layout? So, you'd want to check that whoever was coming to site had maintained that equipment before. There's so many variants out there of switchgear and transformers and auxiliary equipment that you'd want to make sure that they are competent to do the maintenance task. One thing to touch on, Dan, which I don't think we've covered yet, was there any other work, be it electrical or non-electrical, taking place in and around the substation? If we go back to the photograph shown earlier on, the transformer compounds were quite tight to the factory floor. We had some pipe work sort of just above where the transformer compounds were, etc. So just keen to see if there was any external factors that may have influenced what's happened.
Yeah, it's a good point. Especially for work on the network as well. It's a good point because normally, typically electrical equipment's designed to, be safe in its standard operating configuration. So if anything is typically going to go wrong, it's when you're taking it outside of that, maybe so for switching or maintenance. So it's a really good point. There was no work on the network going on. So like from an electrical perspective, there was nothing happening. There was no isolations or switching or anything like that. So nothing on the electrical network. Works on site. There wasn't really any like abnormal production as such. It was standard production runs, which tends to fluctuate in load and things like that. So standard production. I think the only other thing that was going on was there was some construction work on the west side of the building, been going on for a number of months. So they were taking in a phased process, taking columns down, replacing the columns for that infrastructure. So there was, mechanical works and building works going on the west side of that building.
I think
any thoughts?
Yeah, I think from an operations standpoint, I think good points on the other works in the air, work on network. In the data center world, we operate off of SLAs, so time responses or various temperature or power requirements. And in production facilities, it's a little different. We talk about the five nines in data centers, like how much uptime. And I'm sure in production, you're worried about the output of the facility. So, you had about 4.5 hours until you got the CCTVs back up, and you had about 6 hours until you said the site was restored. And you
Yeah.
mentioned that you had done all the walks. Like when transformers, especially as you saw that explosion, they failed loud. So, was anyone in the area? Did anyone hear that? Why did we work the way we did through the system? Was
Luckily there wasn't anyone going past. Obviously, you'd seen how much, if someone was in that substation, that they are low frequency events on the low frequency but high consequence. So, luckily,
Yeah.
touch wood, and
Yeah,
again,
thank
no
goodness no one
impact.
was around. If you're ever unfortunate enough to be anywhere near a transformer, you know it when it fails. It's quite loud and it's very scary. So that's great. And then with actually that'll go. We'll cover that in environment. Actually, my next point. That's all I got.
Okay. Yeah, it's fine. And just quickly on competency, like I said, we assessed the third party contractors. Um, in other people on the network, authorized persons who were operating and switching, they would have been assessed following an internal process. Um, Competency of people doing the inspections internally. I mean, there were technicians, time served LV technicians, or they'd been upskilled to, do those inspections, I guess. Familiar, maybe not fully with HV, but enough to, get by doing that element of it. I'll just brush over. I'm just conscious of time. I'll kind of brush over measurement because we didn't really have a lot, if I'm honest. So some considerations that you might have in there, metering. So sometimes you do have metering that's there that you can interrogate. That might give a indication. But this was an older area of site, so there wasn't really any metering to talk of. And similarly, condition monitoring. There was condition monitoring on a area of site, but not this particular area. So there's no data to jump back into as part of that. So the environmental elements of this, these are some of the things that we looked at. And again, temperature. It was June, so maybe warmish, but not red hot. We had the odd hot day here and there. Humidity, I know wasn't a factor because the we did have humidity detection in the adjacent building because you kept product in there. So that was something that you needed to keep an eye on. Leaks, I'm not sure. I like to think nothing got into the box from outside with it being compound filled. But again, because you can't remove the cover, they can't really verify that. And maybe something from in out, so maybe oil coming through the bushings. I'm not sure, but there's no indications externally. An IP rating. Again, that IP rating probably was quite verified with it being a compound filled box in there. You got
Yeah,
anything to add on there?
no, that's pretty good. I think the only other thing I would add is, you know, you showed in the overhead view that this transformer that failed was right next to your high pressure steam lines and
Yeah,
condensate lines going through that. So that can definitely be a consideration in my mind. Like, did one failure
definitely.
lead to another?
Yeah, yeah, definitely worth looking at in as part of this. Um, so I suppose um whilst we're on it, then I'd definitely, a metering, condition monitoring wouldn't come into it. Temperature, unlikely. IP rating. So this is I suppose just to give a bit of context around some of the other bits on there. This is the latest oil sample. This is the transformer characteristics. So you can see it's a 1987. So although it's not a spring chicken, there's still plenty, and you could argue that's past its operational life to be 25 years out of an asset. But from experience, there's still plenty. She's been maintained. There's still plenty of years in the old girl, I would say. And this is the latest oil sample result, which was, what was that, 2 months before the failure, a month before the failure, which again, there's no indications of anything that was, it's aged in line with the age of the asset. There's nothing stands out there to say there's anything wrong. So from that side, I'll probably drop off the oil sample side of it, but maybe keep on age of assets, possibly it's a consideration, but nothing indicated that it was degrading to that point. Latest maintenance point, so for the circuit breaker and the transformer, and again, I know they're very generic checklists, but to go back to one of the points that was made in the chat, the actual maintenance kind of consisted of so the circuit breaker was withdrawn, mechanical maintenance done on the circuit breaker, testing on the circuit breaker, and then that circuit breaker put into the circuit earth position, so grounding that circuit, maintaining the transformer, and then on completion, it was an IR test from the circuit shutters down to the primary windings. So there was a 5 kV IR insulation resistance test done as part of the maintenance, which was done like the year before. And there is
the certificate for the battery tripping unit. Does that form part of this?
I don't have the certificate for the battery tripping unit, but I saw it done like the year before.
What did maintenance look like on that?
So that was checking the batteries, so the voltage on the batteries. It was an old set of batteries, so you had a supply, a fused spur. There was no supply indication. It was just an isolator on the batteries. They tested the voltage, cleaned them down, things like that, and tested the float voltage. And then on the maintenance, tested the output current to make sure there was enough current there to operate the electromechanical relays, which was, I think, it was around 2 amps or something there. I don't have the manual. I don't have the cert for it. So we'll keep that on there as a consideration. But I'm pretty sure I watched them do it. But like you say, if you've got no records of it from an audit process, we can't disprove that it wasn't the battery tripping unit. Power quality. So about 18 months before, I'd had a power quality study done on this asset. So, I mean, this is a typical week and nothing has changed on the network. So from an 800 kVA capacity, the load sat at around 350 kVA, which again is quite a good load. And I know it's not all of the power quality elements, but the worst bit was probably, when you're looking at the LV side, the THDV. And we normally have a 4% limit in line with G541 from an ENA standard in Europe. And it was always below there, apart from the odd little spike above 4%. But again, nothing to kind of write home about. So I would take loading off. I'd probably take power quality off. I'd be happy with that. Coordination. So again, just a snapshot, but we had the coordination, protection coordination study done. That was in place, and we'd had the trip time testing done on the switch gear as part of the maintenance. Again, that was individual, so it was one at a time. We haven't verified the whole board, so maybe there's some areas that need to be verified, but fairly happy that those settings are in place. And then this is an example of the inspection sheet that the guys do every 3 months. So you'll see here, I mean, the last one was done 3 months before the failure. If I wanted to kind of focus on the area that we've left out is, so the 110 distribution, the battery charger, and that's the record saying that it was checked. Anything on there? Happy with that? Good. Why is it not moving on? Yeah, so but I guess on those inspections, was there anything? Yeah, so on those inspections, it's a visual. They'll have a look at the batteries, and I think they'll check the float voltage. So that check the 110 on the test function on on the batteries that were there.
To
So whilst
confirm then
I'm
that the tripping
yeah,
circuit wasn't tested, that doesn't form part of the battery maintenance.
on the maintenance, they just tested the no, they just tested the output from the batteries.
Okay.
And then on the inspections, they just do a visual. So they'll check the like visual check of the batteries and then check the float voltage by pressing the test button on the battery set to make sure you've got 110 available there. So I guess at this point, um, we've got to a point here of why the transformer failed. We've got a couple of things that are left on. Um, Probably took off quite a few there. So what I've done is I've got in touch with a vendor who does who will do survey work and do forensic investigations on electrical or mechanical switchgear or failures. This one was switchgear specialists. So I got them to site to have a look at trying to help determine what's gone on and what basically I don't think we're ever going to understand why this actual transformer failed. The transformer was the area that failed, but there's nothing left. So there's no, you can get some really good outputs from forensic investigation. But essentially the feedback I was given was, it possibly could have been humidity, could have been linked to your maintenance activities, could have been from leaks, but because there's nothing left, it's very difficult to try and identify what that is. For the age of asset, could that have been linked to it? Obviously, we've covered a lot of things that could have been. I think the big thing for me is from a safety perspective, why did that protection not work as expected? So if we look back at this, what sort of things should we be looking at?
And if we circle back to the work that was carried out, sorry, adjacent to the transformer compound, do we know if there's any electrical infrastructure, cables or otherwise that run through that part of the building where the works were taking place that may
Well,
be compromised?
well, what I've had to do at this point is because the transformers failed, but I've got to make sure that that doesn't happen again in terms of electrical safety and reliability from that side. So I'm trying to figure out why the protection didn't work. I've gone to check the batteries. When I've checked the batteries, so I've checked the voltage on I've checked the float voltage and I'm getting less than 110. Which maybe there's been an impact from the downtime. I've checked the incoming supply, so the fuse spur that feeds the battery tripping unit, and that's on. I've now opened the battery tripping unit up and I've checked the incoming terminals and I've identified that there's no voltage present. Now, this was an old battery tripping unit. A lot of the newer ones, you will get an indication on the front, and sometimes you get outputs as well that say to feed that into your SCADA system or your BMS to say that there's no incoming charging voltage there, but there's no voltage present. So I presumed the breaker's probably tripped that feeds it when we've had the outage. So I've investigated the supply, likely tripped down to the outage, and I've found that the MCB in the distribution board was tripped. So I've then closed that on and the supply is tripped immediately. So I've now got to try and investigate this further. So I've followed the cable from there. This is where the building works was taking place in the west side of the building. Switch rooms here. And the LV supply comes from somewhere around this area. But I've identified around here that the 230-volt AC supply was severed. Must have been done in the building works. It's been going on for around 9 months or so, and it's been severed at some point in that process. So one of the things that I suppose we've got to look at is, again, always comes into it, competence. So, and it's an easy one to fall back on, but competence of persons. So yes, the maintenance and stuff might have been getting done in line with the standard, and people were competent. One of the things that came out of this was the competence of the persons doing the inspection. They did have an electrical background, but electrical substations and infrastructure wasn't their core discipline. Process, there wasn't a process to follow. So you seen that check sheet, it was a tick box for the 110 and the battery tripping units. So they did follow a guide, but there was no process of what they were looking for, what they were doing, and what tests they should be doing. So again, instruction and training wasn't there. There wasn't a process and the level of supervision to make sure those guys were competent. Um, and I guess the final point, the culture point, when we talk about competence, we're talking about those core disciplines. From a culture perspective, if someone's chopped through a cable, it's that doing the right thing, going and telling somebody that something's happened. And if your culture is not right, or if there's that or blame culture, they might risk, oh, I'm going to get into trouble if we do that. So it might not be an element, it might not be. And you need to make sure you've got that open and transparent culture to make sure people will come forward in the event of a fall. But again, all you would never pick one of these up on its own. So that again, it's kind of like that Swiss cheese thing. This was a head scratching investigation to go through to try and determine how and why it happened. But the battery tripping units are so important. I think I've said it on every session that we've had. I can't emphasize enough how important those battery tripping units are to your infrastructure and your safety. That's what they're there for. Have you guys got anything to add in there?
Yeah, I think you kind of went through it really well. And when it comes to training, they for those older style batteries, you'll depending on the load, even when you do a output test, you said it was only a couple amps. Your flip
Yeah,
your
two
flip
amps.
voltage won't change too much, especially with that minimal load, but it will go down over time. So that would be an indicator like, hey, like my float voltage isn't where it should be, and it seems to be going lower and lower every time.
Yeah,
So, and it's always, is it on or is it really on? Like, is the incoming supply actually on? Those kinds of like little checks in your mind, understanding the systems that you're working on, understanding what the tests are supposed to accomplish. Like, why are we doing this maintenance? Kind of gives it a little bit more insight as to the result.
no, 100%. So I'll just kind of, there weren't really any standard output learning outcomes as normal because it's been more of a learn as we go type session. And it is quite lonely. It's quite lonely being a responsible person on an electrical network. And often when these things happen, you've got so many eyes looking at you from production managers or directors, managing directors, and things like that. And so it can be a lonely place. I've just had the help there of two seasoned industry professionals. So what I would say is definitely be open to feedback and definitely try and utilize the information and experience that are around. There are people out there that can help on site and off site. So do utilize that. And I'll just kind of jump through. So if there are any Q&A, we can try and maybe get one or two in. Um, just a quick mention, we are going to have conferences in the in 2026. So we're going to have one around May time in the UK, which will be like a UK and Europe. And then we will be having one in around Q4 in the USA again. So we'll send out more information on them in the new year, but exciting stuff. If you are interested in attending or if you'd potentially like to speak, again, get in touch, let us know, and we can discuss that. If you want to get in touch, there's our details, but I'll go to Ben now and see if there's anything in the Q&A.
Yeah,
You've
of
got any
course.
time.
So just quickly on a few different parts. So in relation to the fishbone slides, so this is from Paul. Did the transformer fail or did the termination of the cable fail? Were the cables ever IR slash pre sorry, were the cables ever tested IR slash pressure?
Yeah, so they were tested every 5 years on the maintenance. So from the circuit side, that formed part of the maintenance. Once the transformer was done, the switchgear was taken out of ground or out of earth, and then a 5 kV insulation resistance test was done from the circuit shutters down the cables, including the primary windings of the transformer.
Good stuff. This one's from Anthony from our side. So how often was the oil level checked?
That was every 3 months visually.
Yep, good stuff. So this is a share from Dave. So I've had a 750 kVA, 27 kV air-cooled transformer fail due to cottonwood seed entering the enclosure. Annual PM service was performed, but it was before the summer cottonwood bloom.
That's a wild one.
that has got
That's
to
like when
be
you
a
hear about a
US
squirrel
based.
or something getting in your system.
And then just final one. So this is from Jose. For the corrective action session of the webinar, are there any of the same transformers on site? If so, what measures have been taken to ensure the same issue does not happen again, i.e. more frequent temperature IR measurement of the junction box, protection type relay installed, etc.?
Good point. So what did we do differently, I guess? Yes, so and from an inspection perspective, there was a lot more onus on training and familiarization. From a inspection side of things, we talked about partial discharge earlier. There's a number of different tests that you can do. So depending on what your kit is. So on that one, because it was compound filled, they were just doing a TEV test, which is probably your best indication. But they did also then include ultrasound on there as well in future. So every 12 months that was included. Um, Maintenance wise, I mean, they were never going to invest in changing out the protection, but it did form part of a standard to say, as new circuits were added down the line, to have an an electronic relay, including arc flash protection as part of loss prevention and risk management. But that competency of the persons to make sure that we'll do, because the transformer failed. I don't know why that actually happened. It could have been anything down to that aged process. But the actual, if the protection had worked in the times that it was tested to and it was set to, the damage would have been a lot less. It probably wouldn't have blown out of the junction box. It would have had a fault and tripped within milliseconds, as opposed to 3 to 4 seconds on that circuit. So the batteries were a big consideration and then due diligence around them. Yeah, was there anything else in there, Ben?
Sorry, on mute, rookie mistake. So final one for Richard Henderson. This is going back to the SLD. Did a second breaker fail to trip, resulting in the main site incomer tripping?
Yeah, the incomer. So the feeder for that transformer didn't trip. Then the next setting was the incomer, but that was also fed off the same set of batteries because it was in the same substation. So the fault essentially went nearly a kilometer back to the primary substation. That's where the protection tripped because it was on a different set of batteries. That's why it took so long to trip.
That's it from my side. Thank you.
Brilliant. Well, no, thanks very much. I know it's an odd one to end the year with, but it's been great doing these every month and hoping we're building a bit of a community where we can feel safe sharing these practices and getting inputs from each other because you've only got as much experience as what you've got, and there's lots of people around you who you can tap into, and hopefully part of this community shows that as well. So I appreciate your time, everyone.